is numerical integration and differentiation. I don't know whether we'll be able to go to differentiation or not today, but we'll be starting with differentiation and integration and concept of differentiation, okay, how they can be calculated numerically. As we have discussed at the very beginning of our course, that numerical techniques are actually not intended for problem integration. It is developed because we have many practical problems. Many means most of the practical problems that involves many practical scenarios cannot be solved analytically. For this reason, we need numerical methods principally. But later, when we become very much what we call dependent on computer, you are developing a method to solve a complicated problem that will always include the simpler problems in it. For this reason, actually, what you need to do, you have to start with a very basic something. If you do not know the principle of calculating derivative of a function or integrating something, you will never be able to convert it to start with a very simple something. Okay. When you have been introduced with a derivative of a function that we discussed many times in this course also in earlier classes, what have we done actually? Is it not that derivative is sometimes maybe called as a slope of a point of a function at a particular point?
Yes, sir.
Okay, can you give another name of this slope?
Rate of change.
Is it not rate of change of a function with respect to the independent variable? Yes or not?
Yes, sir.
Yes, sir.
For example, say if you have a function y equal to mx, we are using this thing in a general form. If your x is here and we have our y there, and you know that the relationship between x and y will take the form of a straight line, isn't it?
Yes,
So
sir.
if you want to find the rate of change, then what you can do? You can just consider a small length, for example, with del x, and that will give you a small variation of your function del y. Then we can easily calculate the rate as del y by del x, isn't it?
Yes, sir.
Would it not be, for example, in our case, if it is your time, and if this quantity is a charge Q, because we are having a very general mathematical equation that we are discussing. But if you want to use it in our engineering, cannot be, we can have this thing related to in this way, that you can replace your x by t and q by y by q. Then this will be equal to a del t. What is it?
Sir, I current.
And this is simply equal to charge. We can call it coulomb divided by second, isn't it?
Yes,
Yes, sir.
Is it not charge?
yes,
And that is the current I. And you see that that current is constant. For example, what is the case? Is it valid for your DC current or is it valid for your AC current?
The DC current.
is what? Reason you see that that range rate of change, no matter where you calculate it, that will be what? A constant something, isn't it? So you are having a current there, that current is constant. Now tell me, if this quantity is given, if you want to go back the original Q versus T curve, how can we go there?
Integrated.
Integrated, exactly. Integrate by if you know that you can say this current is I0, then you can easily integrate it, for example, from a particular, say we are integrating, say from 0 to T, okay? We're not considering this region, so 0 to at any time T. Then you can consider it 0 to T. Then this is your I0 dt, isn't it?
Yes, sir.
And that will be equal to what? I0 multiplied by T,
I see.
isn't it?
Yes, sir.
Yes, sir.
And if your system is carrying an initial current, then that current should be added with it. Consider that our system is that we are 0 with 0 current and 0 charge. In this case, this line will be something like this, isn't it? Okay, now if you want to go back there, this is not the process. Analytically, it is obtainable. But if it is not analytically obtainable, then how you know variable, okay? For example, if we bring our T near here in this direction, your charge will be decreasing. And if we bring our T in this direction, your charge will be increasing, isn't it?
Yes, sir.
Yes, sir.
Now, is it not, for example, consider that we are subdividing this interval into a smaller numbers of times, smaller intervals of times. Say this interval is del T. All are equispaced, okay, del T. Then can we, for example, is it not, for example, okay, forget about this. If we consider this quantity, is it not the current multiplied by a small time del T?
Yes, sir.
Yes, sir.
Okay, fine. Then if we want to just replicate this thing here, consider the first rectangle. Is it not equal to I0 del T
Yes, sir.
area? Is it not the area?
Yes, sir.
Yes, sir.
Then again, if we go to the second area, it is also equal to I0 del T, is it not?
Yes, sir.
Yes, sir.
So if we go all the way, say up to a certain time del T, then your I0 you can keep common. Then you have your del T plus many numbers of del T, say n del T. Then is it not the total time? Then you can
Yes, sir.
easily say that this can be equal to your I0 T. Okay, and you see that as you are increasing the position of T, gradually, linearly, you are adding for, if you consider it at the beginning, this is what your value, you can consider that if you plot it, say this is your del T, at 0, no value, at this is your del T, you have a value. Again, you are adding on top of it another value, but not at the same time. At say 2 del T, you have another value there. At 3 del T, you have another value there. At your 4 del T, you have another value there. If you connect them together, it becomes a straight line, isn't it?
Yes,
Yes,
sir.
sir.
But then what is actually happening there? You are simply calculating the area under the curve. What curve? I0 curve between the limit 0 to T. Is that clear?
Yes, sir.
For this reason, actually, in general, what we do, if we have a curve fx dx, this integral is nothing but the area under the curve, area under fx between where to where?
A
A
to
to
B.
B.
X equal to A to X equal to B, isn't it? So in this case, you see, if we consider the previous example of our charge and current in a DC circuit, you see that that area can be calculated by simply adding up the small area of the rectangles, isn't it?
Yes, sir.
Fine. Now we consider a situation where, say, your current is charge is changing in this fashion. Your charge is changing in this fashion, for example, say. not a straight line. In this case, what we can do? Consider that we have this point A, B, and here we have this point A. Okay, your X is equivalent to say X, and your Q is your Fx, because this is your Qt. You got the point?
Yes, sir.
Okay, fine. Now tell me, if you want to proceed in this way, what you need to do? This is what the width of your starting and ending point. What you can do, you can divide it by n. Then what will happen? You will have some segment there. Okay, say this is 1, this is 2, this is 3, something like this. Okay. In this case, what you can do, in order to calculate, you have to calculate the area, isn't it? You have to calculate the small areas. If you want to calculate this small area, you see that your function is varying. Consider your first segment. Okay. In the first segment, say we are dividing it by equal segment equal to say h. Then what will happen if we draw or enlarge view of the first segment? This is your a. Say this is your a plus h. Something like this. You see that this width is equal to what? Is it not h?
Yes, sir.
And your function is changing, for example, in this way between these two points. Now tell me, in our earlier case, we considered it as a rectangle, isn't it? If you want to consider it as a rectangle, then that rectangular area would be equal to what? FA multiplied by H, isn't it?
Yes, sir.
Would it be a correct result then?
Sir, if H is significantly large, then it won't be a correct result.
Okay, fine. Very good answer. If your H is significantly large, then that error will be huge. And if it is small, then your error will be less. Okay, this is one thing. That means we can refine our approximation by changing the value of H. You know, from your very basic error calculation earlier, at the beginning of chapter 4, we have seen that we have two types of errors in general in numerical computation. One is called truncation error, another is roundup error, isn't it? And
Yes, sir.
you have seen a plot there. That plot says that if we increase the step size or decrease the step size, your roundup error is actually decreasing. The reason is that computer has a machine epsilon, that means the least possible number that it can store. Otherwise, if you go beyond this, it will be truncated to 0. So rounded up to 0. Okay, so a roundup error is there that actually very much pronounced in the case of smaller numbers. And we have a truncation error that is there in the formulation when we are approximating something. As you know that we have discussed that thing earlier, that when we are want to calculate the derivative of a function by using a first order approximation, it is nothing but approximating your function by Taylor series, isn't it? And disregarding the higher derivative. So as a result, some error will always be there. So these two errors join together, and the error curve looks like a what? A bell-shaped curve will have a minimum point, and again, if you go either ways, your error will be increasing. For this reason, actually, your minimum or decreasing the step size is not actually a unique strategy, strategy to reduce the error. But in this type of problem, you can easily, but it is to some extent. Okay. Another, can you, for example, give me an idea that instead of using, for example, rectangle, what can we use there, a geometrical shape that will give you a better approximation?
Trapezium.
Yes, very good. That means if we just connect these 2 points in this way, but I have drawn the curve, it is a handwritten draw, actual thing may be different, okay? So you see that we are now having a what we call trapezoid, isn't it? If you want to calculate the area of this trapezoid, how can I do that? You know the function value at this point, this is equal to FA plus H. Then the average ordinate rule can be applied there. The area will be, ordinate average is what? the average of your function values divided by 2 multiplied by the width age. Isn't it?
Yes, sir.
This is the area of your trapezoid. Now you can easily guess that for this particular fictitious example, you see that the error will be much more less than what we have if we consider this as a rectangular approximation. Okay. Similarly, if you have a curve with higher nonlinearity present, then your rectangular approximation will be not a good strategy. Okay. But if we have a curve, something like this, say, we have a curve, something like this, okay? Value of a function, say this is your x, that can be thought as t, and this is your fx. Can you relate it with a practical example
BH curve.
of our electrical engineering?
So BH curve.
Can it be, for example, a voltage across a capacitor, charging voltage of a capacitor VC? VC is equal to E into 1 minus e to the power minus t divided by RC. You got the point?
Yes, sir.
So you can consider this is actually a charging of a capacitor by a DC voltage. Or you can think it as a current flowing through an inductor, RL by R by L, 1 minus e to the power minus R divided by L. You know this thing, okay? In this case, you see that you can have a reason where you will see that your rectangular approximation will not give you good result. But you have a region there where your rectangular approximation is good enough. But your trapezoidal rule is actually a general formula for your approximation, isn't it?
Yes, sir.
The reason is what? If we have our FA plus H, both are, say this is also equal to FA, then is it not equal to 2FA divided by 2 is equal to FA?
Yes, sir.
Then it will coincide with your what? If your height of your trapezoid, ordinate values of your trapezoid, it will merge to a rectangle, isn't it?
Yes, sir.
So your trapezoid rule actually a bit general, okay? By depending on the function values, how it is changing with your independent variable, it will be, it can be a rectangle. So these are the what you call, I would say, a very intuitive way of explaining the integral, okay? But sometimes you see not always that the equation of your curve will be given. We actually use we illustrated an algorithm of numerical method by considering a problem. That problem has analytical solution. The reason is that we can compare the performance of this algorithm because your actual value will be known to you, okay? Or we will apply our numerical algorithm to some physical problem whose behavior is already known to you. Otherwise, you cannot apply your numerical algorithm. The reason is that if you do not have any idea about your behavior of your system, where you are applying your numerical method, you are simply what we call making a blind, for example, a gaze or something like this. That will never work. For this reason, your numerical method is being applied by the people, okay? In practice, those are professionals, okay? They have some professional experience about the physical behavior of your system. As an undergraduate student, your idea should be something like this, that we have to illustrate our problem by using some examples or problems whose analytical counterpart is available as a background or building the basic of our technique, okay? So in your, at the beginning of your chapter 21, you will find some description of the technique. All the things are based on intuitive process. Actually, what you can do or think that before the application of or introduction of your computer, okay, we use some non-computer method to solve our engineering problems. In such cases, a calculator was also not available. Can you tell me, probably I have given some idea about it when computer was not available. We used to have another version of the computer, we call it mechanical computer, by which some calculation could be made to some extent. In such cases, actually, graphical technique is used to calculate your differentiation and integration by simply dividing or calculating the rate of change, or by calculating the area under the curve. For example, say if you have a land and your land has some area, do you know what are the units in which your land areas are actually measured?
Square feet.
Okay, it can be a square feet, it can be a square meter, even it can be acre or something like this. So yeah, there exist many other units, but the generic unit is a square meter or something like that. Then if you have a irregular shaped pitch of land, then how can you calculate the area of the land precisely? If you are an engineering student and you have already learned something about your civil engineering drawing in your first year, and you know the mathematics, then if someone will ask you, even any one of your relative, even from your family, will ask you to calculate the area of a pitch of land whose scale map is with you, can you do that?
Sir, we can firstly take a shape that is as rectangle as possible, and then the abrupt areas there we can take the rate of change to calculate the area.
Rate of change to calculate the area. Will that calculation will be acceptable by someone? Because in Dhaka city, you see, 720 square feet of land costs sometimes 1 crore, even 10 crore rupee, 10 crore taka. You know what is 720 square feet is equal to 1 katha. That is not the usual way of measuring the land in practice in this country particularly. 1 katha of the land in Matizil, for example, cost about what? Sometimes 100 crore taka. If you just make a mistake, they are 1%. How many cost will different there? Okay, try to have a gauge, okay? How to do that? So if you want to do that, actually, when computer was not available to us, but mechanical mechanism was with us by which we can calculate the area of the land. One of the things is that not the rate of change. What you can do, you can have, consider it as a graph paper, okay? What you can do, you can split your pitch of land into a smaller numbers of rectangles or cubes or squares throughout your map. Then you calculate the area of the square and you add them up. That could be some approximation to do that. And the boundary can be approximated by what you call trapezoid, so that it will fit almost nearly equal to the area of the land. Okay, so these are the mechanical or semi, what you call non-computer type methods still being used by the surveyors. Those who are in Bangla, we call them Amin. Okay, it is not Ruhul Amin. Okay, his name is, the position name is Amin. They usually measure the area of the land. Now we will be starting with our basic formulas. Okay, this class of formula is called Newton-Cotes formula, and your technique is very simple actually. And you can easily develop your own conception by using a simple concept of calculating the area that we have discussed a bit earlier. Okay, what you can do, if we have a data point given there, okay, your function may be given, that function data can be calculated. This is one way. Another way is that your function may not be available, your data can be given. Okay, if you have been given with 2 data points, for example, no other things are available, but you know the value of A and B, and the data values are also given. Say this is FA and this is FB. What you can do that, we know the interpolating polynomial, we can connect them by an interpolating polynomial. We know that this will become a linear interpolation polynomial, isn't it?
Yes, sir.
Then if we have another point they are available, you can use a quadratic polynomial or parabolic polynomial. If some other points are there, you can also add another point there. As a result, we know from the chapter that if we have our n plus 1 numbers of data points, we can think of an n order polynomial there. So that will that we can use as interpreting polynomial that is there in the Newton's method. And but we have another technique there, Lagrange's method. We have to discuss about this thing. But this is your interpolation. But if we have our huge numbers of data, then what you can do? If you have a huge data present, then what you can do? One way can be, okay, you just connect this data in this way. Then you put, for example, some trapezoidal there and apply your trapezoidal rule there to calculate the area of the trapezoid and sum them up. In this way, you can calculate the integral or area under the curve. Or another method can be, if we have huge numbers of data there, you just represent the data by a least square curve, okay, that we discussed in chapter of curve fitting. Then if a least square polynomial is available, that polynomial actually will represent mathematically your discrete data. Then that polynomial can be integrated or differentiated analytically to serve our purpose. Okay, so in this way, we gradually go to develop our algorithm in a systematic way. So one first thing is then what? If we have our 2 points, then these 2 points can be connected by a straight line. Okay, this is figure A. Then you can use your trapezoidal rule there to calculate the area under these 2 curves that will be equal to the integral of your function between A to B. And you can easily say that this will incur some error depending on the variation of your function between these 2 data points. If they exactly coincide with your approximated straight line, then no error will be there. For this reason, if we have our data variation that is in the form of a straight line, no matter whether it has a slope or not slope, in all the cases, that integration can easily be done with 0 error by using trapezoidal rule. But if we have our function that has a nature that is not equal to a straight line, that is there in figure A, then what will happen? This blank area, hashed area will be the area you are calculating, the approximated integral, but you have your area left there, that will be error. Similarly, the error can be improved by if we select another point in between A and B, then we have our 3 points. Then instead of using a straight line, we can use a parabolic curve or a second order quadratic curve there. If dashed line is your quadratic curve, you calculate the area under this quadratic curve. Then you can easily see that how your errors is improving. And another issue is that you can subdivide your region A and B. Then you can apply your first order approximation, the straight line one, so that again your error can be reduced. But if you, the reason is that if you want to apply higher order polynomial, interpolating polynomial, then what will happen? You have to find the interpolating polynomial first, then you have to integrate it. So in order to avoid this complexity for higher order cases, you can also have an alternative, something like this. You can subdivide your interval between A and B into many equispaced intervals. Then each of the intervals can be dealt with the trapezoidal rule, and you can accumulate them or sum them up to calculate the integral. So in this way you can go. So the first version of your Newton force formula is the trapezoidal rule. I have already discussed. It is nothing but the area of the trapezoid between the points x equal to A and x equal to B. How to calculate it? You know it. So equation 21.3 is the area of the trapezoid between point A and B, and your function value f A and B. You know that this is the average ordinate rule, because you are simply averaging what?
Averaging the function values.
Averaging the function value from where to where?
F of A to F of A plus H.
F of A plus B. This is sometimes equal, you know, in geometry, the x-axis is called abscissa and your y-axis is called ordinate, okay? So you see that if we have our x equal to A there, x equal to B there, you have a function value there. This is your FA, and you have a function value there. This is your FB. We are assuming that in between them, your function is changing like this, but in reality, your function may change in a different way. But for this region, we have our error there, that this area is simply equal to you have your ordinate averaged, okay? Then multiply it by the width B minus A. This will be the area. Or you can go in the different way. Eventually, you will arrive in the same equation. Okay, you can calculate the first the rectangular area first, FA into B minus A, then plus equal to half into what? Half into B minus A multiplied by FB minus FA. Isn't it?
Yes, sir.
This is what the area of this triangle, and this is what the area of this rectangle. Okay, you can add them together, you will find this thing. So you have your trapezoidal formula for integration is with you. Now that can be applied, for example, multiply, or it can be applied singly. If we have a data, okay, let me discuss the things are there in your book nicely described, but still I need to recap it for your understanding. Okay, if your data is changing in this way, say this is X, this is fx, or your data can be something like this, it is changing like a straight line in this way. Okay, in both the cases you see, okay, your trapezoidal rule will give you exact result, okay? No error will be there. But if we have our data, for example, changing in the, an example is there, you can have a look. Okay, say your data is changing in this way. Between the limit, say this is your x equal to A, this is your x equal to B. Okay, now you see that your height or nearly same, isn't it? Your FA is nearly equal to FB. Are not it? Are not
Yes,
there?
sir.
In this case, the trapezoidal rule or your rectangular approximation will give you the same value. Okay. Now this hashed area will be the area, isn't it? Can you imagine that how much error will be incurred here? Because this area is
More than
excluded from your
50%.
calculation. Okay, more than 50. In some cases, even it can be much more than this. Okay? So if we consider, for example, a single segment between limit A and B, but you can also, if the situation is something like this, then what you can do? You can again subdivide it, the region, into a smaller number of A's. Can you do that?
Yes,
Then
sir.
this can be considered as one trapezoid. This is another, this is another, this is another, this is another. Can you imagine? You can easily say that the latter case you will have minimum error, isn't it? So your trapezoidal rule can be applied singly, or it can be applied multiply. Multiple application is needed if we have our problem that is very nonlinear and have this type of wide variation between these two intervals. Okay, derivation is there. You can easily calculate it. This is described there. I will not go into this. This is what your approximate. This example is there actually what I have discussed. Your error approximation is there. You try to look at it. How to calculate the error example is there. But this error calculation can be calculatable only when you have your function. What is happening? Are you seeing the screen?
Yes, sir. You are sharing the book.
Yeah. The reason is that when I am annotating them, I have to switch between view mode and annotation mode. Otherwise, it cannot be scrolled. So is it not the thing that we described a bit earlier? Okay, you can take a look and even you can prove it or calculate it or verify it. Okay, your function value is given. Okay, if you plot this function between the limit x equal to 0 to 0.8, you will see that this is what the variation of your curve. And you have been asked to integrate this function between limit x equal to 0 to x equal to 1. You can easily imagine that what will be the error, okay? You see that almost you will get nothing because the value of your function at these 2 points is very small in compared with what? The actual variation of your function, isn't it?
Yes, sir.
And the next thing is what? You can improve it by subdividing the interval between 0 to 8 into say another. Even you can go, you can have an exploration by your own, going beyond this example. Okay, these things are there described. You can redo it, but summary is given there. Okay, I have already discussed about it that if we use the subdivision, then how the result will improve. Okay. So we have, in that case, we have to use our trapezoidal rule in each of the segments. Then we have to add them up, and the derivation is there. If we put them into a generalized form, it will take the shape of equation 21.10 that can easily be implemented in computer, and the error will be here. Okay, it is in the order of, you see, error will be very small. Now the thing is that if we want to just for this function, if we apply trapezoidal rule multiply, then you will see that this is the result. Okay, because calculation will take time, but it is not very difficult to do. Okay, so you see that if we use only one segment between x equal to 0 to x equal to 8, you can choose a function, for example, like our current flowing through your capacitor during charging phase, or current flowing through the inductor for a DC current, transient and steady state both included, or even you can consider the BH curve. Okay, can anyone tell me what is the area of the BH curve? If we have a BH curve, and that BH curve will have an area,
Sir,
and in which, how is it related to physical something?
Sir, mu, permittivity.
আরেকজন বলো তো দেখি, is there anyone who can answer differently? The area. এই বাকিগুলো কি ঘুমাইতেছে নাকি? হ্যাঁ, একটার মুখ থেকে কোনো কথা বেরোয় না। If we have a BH curve, something like this, if we consider a small area there, this is what that area, okay? And this area, this height is delta B, and this is your delta H. Delta B, it is a rectangle, the area will be delta H. Can you tell me what is the unit of this area? What is the unit of H? এত টাকা খরচ করে দিয়ে ইউনিভার্সিটিতে ভর্তি হইলা, এত টাইম ব্যয় করলা, তার
Sir,
রেসপন্স কি এরকম হবে?
Sir, ampere per meter, sir.
Ampere per meter. Is it H?
Sorry, sir, এটা আসলে অন্য একটা বলছি, স্যার।
ইন্টারমিডিয়েট লেভেল থেকে এগুলো পড়ে আসতেছে, তার রেজাল্ট দিস ইজ অ্যাম্পিয়ার টার্ন পার মিটার। And what is the unit of B?
Tesla.
Tesla. Okay, very good. And your Tesla is equal to what?
So Weber per meter square.
Weber per meter square. Very good. So what is the unit of del B and del H then? Weber per meter square multiplied by ampere turn per meter is equal to Weber ampere turn per meter. Unit is Weber ampere turn divided by meter what? Cube. That means some volume is involved there. It is something per volume, isn't it?
Yes, sir.
Now tell me, when we discuss about B and H. Yeah, physical something. Is it not a pitch of iron or something like this?
Yes, sir.
And that will have, for example, most simplest shape can be something like this, a bar magnet or something like this. You have a iron bar, and that contains some numbers of turns, and you are measuring, you are varying the current there I. This is n numbers of turns, then your ampere turn H is equal to Ni. Okay, then Ni divided by meter. Then what you can do, you can easily plot the flux by changing the value of current. Then you can plot this, it will take this form. That means this system involves something that has a volume, meter cube. If it is meter cube, this is Weber. This is ampere. This is turn. Forget about turn. Consider that Weber ampere. What is your Weber? What is the unit of Weber ampere?
Sir, it is phi.
ফিজিক্যাল থাকলে তো মনে হয় একটু আরো বেশি রাগ করতাম, ইন্টারনেটে রাগ করতে পারতেছি না, রেকর্ড করতেছে তো এগুলো পরে ভাইরাল করে দিবে আর কি, তাতে যদিও কিছু এসে যায় না আমার, আর ধরতে পারলে তো খবর আছে। হ্যাঁ, এইটা ওয়েবার। ইজ ইট এরিয়া, ইজ ইট এরিয়া or the unit of current ampere?
Oh, sorry, sir. Just...
Okay, try to gauge it. But those, everything that you learned earlier will be the content of this course. Be careful about that. I will never
I
set any.
to AB ওখান থেকে স্যার মানে ভুলে এরিয়া ভাবছিলাম স্যার।
সব ভুল তো আর ভুল হওয়া চলবে না, ছাত্রদের ভুলের মাত্রার মধ্যে থাকতে হবে। বি কেয়ারফুল অ্যাবাউট দিস। কেমন? ক্যাজুয়ালিটি আমি খুব বেশি পছন্দ করি না। ইঞ্জিনিয়ারিং ছাত্রদের বেশি ক্যাজুয়াল হলে অসুবিধা। ইতিহাস বাংলার ছাত্র হইতে পারে, কারণ তারা সারাদিন স্বপ্ন দেখে, আর ইঞ্জিনিয়ারিং ছাত্ররা স্বপ্ন বাস্তবায়ন করে। কেমন?
জি স্যার।
So this is your area. Akibara, how you see that your things are improving? You can apply this example because we arrived at that point. The reason was that I am always giving you the emphasis that you relate your quantity or method or theory to your engineering. Otherwise, your learning will never be complete and you will never feel the significance of learning mathematics. And that's why particularly the engineering students are very, very weak in mathematics. Although the mathematics is the language, they always think that in mathematics is a non-departmental subject. Okay, no matter we do not want to learn it. But the problem is that without mathematics, you cannot move an inch. So you can calculate the area under the DH curve. Even you can calculate the area and under another what you call a curve that you encountered in your electrical engineering. Okay, then you can change the number of segment. Then you can find the integral and try to find how errors are changing in accordance with the number of segments you are considering in your calculation. In this particular example, it is a very severely nonlinear function. And you see that if we consider only one segment, your error was 89% or something like this. Then if we add another segment there, the segment size was 0.04 H, then that result and error be percent, and gradually improve there to go to the 10. You see that it is reduced to 1.6%. Okay, your error from the earlier stage, you can plot the error and you can easily find in which trend your error is changing with your age. Okay, I will just ask you to redo this example by using MATLAB and draw a plot error versus H and try to relate it, how your error is related to step size. And even it can be related to N, because N and H has some interchangeable, what you call, interpretation. In one of my earlier classes, I have given one problem to you, but you did not heed into it. This is your choice, okay? If you want to go through it, you go it, and if you want to discard it, no problem. This is what another example that I am emphasizing. Okay, you see that this is a parachute example. This is very relevant to the mechanical engineers. Okay, but you know that this type of equation we frequently encounter in transient analysis for a RL circuit excited by a DC voltage, or in an RC circuit excited by a DC voltage. So try to find this significance of this thing. Okay, here you see that your V is your velocity, and if we integrate it, what will be the thing?
Sir, can you repeat the question, sir? It would network.
If we integrate the velocity,
Yes, sir.
what will be the thing?
Sir, distance, sir.
It will be distance, isn't it?
Yes, sir.
So if we can relate, for example, this problem with our electrical engineering problem, say we can have a problem related to engineering is I equal to say E divided by R, 1 minus e to the power R divided by LT. What is it? Is it not the transient current flowing through an inductor if
Yes,
it is
sir.
excited by a DC voltage? Is there any difference mathematically between these two functions? Mathematically,
No, sir, they are similar, sir.
they are similar. Okay. If they are similar, then if we just make an equivalent, that we are integrating V is equivalent to I. Okay.
Yes, sir.
In this case, by integrating our V between two time instant, we are getting, for example, D. Okay. And we know that if your velocity is uniform, your D could be V multiplied by T, but in this case, it will not be the case, isn't it? This
Yes,
is
sir.
for your uniform velocity, isn't it?
Yes, sir.
But your velocity is changing with time. So this equation, for this reason, you have to integrate it. Okay, fine. Now, if we integrate current, what you will get?
Charge.
Very good. So you will get the charge. Okay. And you see that as your current is not changing in a constant fashion, so your charge will also be a time varying function. Okay, very good. So you can easily calculate the charge. Similarly, if we have our voltage across the capacitor, you know that charging phase is 1 minus e to the power minus t divided by RC. Okay. Then if we integrate voltage in this case, what will happen? Is there any meaning or something like this? For example, if we have a constant voltage, E, we are integrating between 0 to E, you will get ET, right?
Yes, sir.
And if it is ET, then how it can be related to a physical quantity? It becomes, your voltage is equal to what? The unit of voltage is volt, isn't it?
Yes, sir.
Your volt is equal to what? Is it not your joules per coulomb?
Yes, sir.
Okay, you got the point.
Yes, sir.
Because your volts is joules per coulomb. Work done per charge is equal to voltage, isn't it?
Yes, sir.
And your time equal to what second? Is
Joule
it
second per coulomb.
joules second per coulomb? Okay. Or can we? Someone has probably make his camera on or something like this. Okay. Or frequently it is changing. Okay? Now the thing is that if we have our joules second, can we write this in this way? Joules divided by coulomb per second.
Yes, sir.
Then what will happen then? It is joule,
Joule per ampere. Sir.
ampere.
So it is like current density.
Okay, in this way, actually, physically, it cannot be related to any quantity unless you multiply it with something, okay? You got my point?
Yes,
Only
sir.
when we will have a meaningful something there. So whenever we are doing something mathematically, they may represent some equation. We can have some result, but you have to interpret it with physical something, okay? Because time is related to us. If we have work done, it will be by some way or other related to energy or work done. So in this way, you can proceed. Now I am hungry actually because I am taking class from 10:30 continuously around 2 hours or more than 2 hours. Have you heard about this rule earlier?
No, sir.
But I asked this question to section A. 2 or 3 students actually answered that question to me, and when I asked them when you have learned it, they said that we learned it in the higher mathematics laboratory. From where you are? In intermediate college was what?
Sir, Raju College.
Raju College. Okay, my daughter was also an alumni of the Raju College. You need to do any laboratory in your higher mathematics elective?
Yes, sir. We did, sir. Like the bisection rule, this type of thing, sir. But sir, in Simpson's rule, this I came to know in admission time, but I did not explore it that much, sir.
Is there anybody, because you are only one responding, is there anybody who can tell me about it? এরপরে ক্লাস থেকে রোল নম্বর ধরে জিজ্ঞাসা করব এবং ওইটা and that performance will be added with your class test. এরপরে ক্লাসে প্রিপারেশন নিয়ে থাকবা, যে কোনো প্রশ্ন জিজ্ঞাসা করতে পারি from your past. So your Simpson's 1/3 rule is another version of calculating numerical technique, calculating the area under a curve, okay? And actually in Newton's first rule, trapezoidal rule, we consider the connecting point as a straight line. Here the Lagrange's polynomial is used, and we are not going to deep detail into derivation. Ultimately, you will be arriving at an equation equal to 21.14. This is also some averaging technique. It is called Simpson's 1/3 rule. Your h is the step length. So if we consider that the region between A and B is considered as a single segment, then your equation 21.14 will be the integration values. But in many of the cases, it is also improved version of your trapezoidal rule. And you see there are 6 function values are involved there. As a result, it can again be represented by equation 21.15, and you see that it is the average height. That means 6 function values are involved. In trapezoidal rule, how many function values are involved?
Sir, 2 function values.
2 function values. So in order to apply 1/3 rule, Simpson's, you need additional point. Okay, otherwise you cannot do that. Now it is called 1/3 because 3 is there. For this reason, it is called 1/3 rule, the factor. Okay, but a multiple application of Simpson's rule is also possible. The reason is that if you have our 3 points, spend your total with B to A, and if it is coarse and the variation of your function is very huge within that region, then still you will have some error. For this region, you can make a finer vertical segment. That means you can add more segments in your width. As a result, you have to apply your Simpson's 1/3 rule multiply there, like trapezoidal rule. That will certainly improve your calculation. Okay, these things are described in this example. Try to redo it. The multiple applications of 1/3 rule is there, and you see that a segment between x equal to 0 to n. We are considering that we have our n plus 1 numbers of data points. between B and A and B, then from A and B, then what you can do, we can subdivide the region B and A by n numbers of segments. Then each segment will have a width equal to S. You can easily identify that in this algorithm, actually, we are using equidistant what you call segments. Then the first segment will be from x equal to 0 to x1. X equal to 0 means the value at the beginning. X equal to n means the value at the end. So we have to apply that. Then the question here, then the thing here is that between x0 and x2, how many data points you have to have in order to apply trapezoidal one-third rule?
Sir, 6 data points.
Because you need 3 points, isn't it?
Yes, sir.
If you need 3 points, then between x0 to x1, you need another intermediate point, okay? So that you can apply the thing there. So gradually what we can do, you can take 3 points, then we can move, okay, just let us illustrate the process. Okay, although it is very simple to be realized, let me tell about it. Okay, what is it actually? You see, that means 3 points are involved there. One is x0, another is x1, another is x2. Then in this case, how many points are involved? That means the end point of your first segment is involved in the second segment, isn't it? Otherwise,
sir.
they will not be connected. This is your x0, this is your x1, this is your x2, isn't it? Then another point is there, x3, x4, x5. Okay, then we'll have this point there. Then if we want to calculate we involve these 3 points to calculate Simpson's rule for the first segment. Then if you calculate the same thing for this segment, then what will happen? This x2 will also be involved there in the second segment, isn't it?
Yes, sir.
So in this way, you can proceed further and make it general. If we make it general, it will take a generalized form, and we can proceed with it. This is how the general form, okay? So this is your one-third rule. We have another rule there. It is called 3/8 rule. In this case, another point will be involved there, and your algorithm will be there. Equation will be there 21.8. And you see that in this case, how many points are involved? 4 points
4
are
points.
involved. Okay. And altogether, we'll have 8 function values involved. 1 at f0, 2 at f1, 3 at x2, and 1 at x3. Altogether 8. So your average height will be equal to all this sum divided by height. It can also be implemented in a multiple way, so that you can do this thing. So with this thing, I want to close my lecture today, because I am so tired that I cannot actually continue further.